So thank you for staying here till before lunch. So I am going to speak about ultrasonic fatigue testing, introducing tension torsion, loading in a medium carbon, and also a lower steel. So this is the summary of my talk. I will start by putting here some cases where very high cycle fatigue happens, even if it is not initiated in conclusions. After, I will present our approach for studying very high cycle fatigue based on ultrasonic fatigue testing, and I will make the most part of my talk talking about tension torsion testing with shear axis test ratio. How we can do that. So we all know that fatigue begin with railway transportation, and this was the first accident related with fatigue, and at the time nobody knows what happened, but happily August Wöhler in the 19th century has introduced to us the concept of endurance fatigue and fatigue limit, but we know that this is not true, and happily we have many failures below the so-called endurance fatigue limit, and the question that we have posed to ourselves is endurance limit a simplification to the testing limitation that was happened in the 19th century, not early 20th century, or is really a material characteristics? So what tools we have in order to test fatigue limit? So we have classical machines for making till 1 million, 10 million cycles, and after we have the question, is there a fatigue limit? There are many papers by Claude Battiaz or Pitel where this question is trying to have the respective answer. So, but going from here to there is quite difficult because we have several situations. I will present here three case studies where this is not a very high strength steel like those ones where the crack initiation is in inclusions, but this is the low alloy steel, but high strength steels. For example, this is a cylindrical head studs that in engines, marine engines, and you can see that we approach 10 power 9 cycles. 1, 2, 3, 4, 4. This is not a very old engine, so it has 6 years, so there is overload on an engine. The second one is that one, where here we have bending and torsion, so multi-axial loading, again, more than 10 power 9 cycles. This is not a very old engine also. And the final one, this one, where two propeller shafts that also broke, and you see that there is no overload because the fatigue region is very high. And again, we are approaching 10 power 9 cycles. So how can we solve that? How can you determine if there is the endurance fatigue limit or there is not the endurance fatigue limit? So the classical way is that one, servo-hydraulic, resonant testing, increasing frequencies, but indeed, we thought that the solution is indeed ultrasonic fatigue testing. We can make 10 power 9 cycles in 1 day or 10 power 10 cycles in less than 30 hours. Of course, we have many problems because we have the strain rate effect, we have the temperature effect, and very important, we must have the data acquisition in order to control the test relating to temperature, loading, frequency, etc. So that's why the machines normally are composed of a piezoelectric actuator working at 20 kilohertz, a booster, an horn, and the specimen, and we have all the things that cooling, temperature measurement, laser measurement. Normally we put also strain gauges here, and we have the data acquisition system that everybody has presented before. And the idea is to have everything in the resonance, either the piezoelectric actuator, the booster, the horn, and the specimen. So for axial loading, this is quite standard already. It's quite standard already. That's why I am not going to explain this. What we want to do is this. So uniaxial, we do not care much more about uniaxial. 2 days ago, our colleague Diogo, we worked with us, talked about ultrasonic fatigue testing of cruciform specimen. We have compression tension, and we have tension with some problems with tension. And now I will present this, the tension torsion solution that we have. And this afternoon, Pedro will speak a little more about this, the technology that we have in order to have this. So this is our machine. So it seems complicated, but it's not complicated because the machine is only that and only that. All the rest is the standard gauge acquisition, temperature measurement, laser measurement, and controlling. So we have 2 machines here. This is our laboratory. We have 2 machines. And what is important in this that we are making either cruciform specimen, either torsion specimens, or uniaxial specimens, or tension torsion specimens, always with the same piezoelectric actuator. We only change the horn and the specimen. And we can see, I'm not going to speak about the tension torsion. You can see our specimen tension torsion. We have 3 throats, 1, 2, 3. So this is the solution that we have for tension torsion. Why we have 3 throats? Because, see, of course, everything is resonance, either axial or torsion. And as we know, the shear modulus in torsion is about 1/3 of the Young's modulus. So we must look for the eigenfrequency in torsion that relates to that. So we have maximum torsion here, maximum torsion there, and maximum torsion there. But axial, the maximum is over there. So what is interesting for us is only this zone. So this is the solution that we have. So we have the piezoelectric actuator, we have our horn. So we make grooves over there in order to transform the axial movement in axial and torsion and rotation. And after we have here the solution with the 3 specimens in order to have everything in the resonance, either rotation or axial. So we have as we know, of course, we here in this throat and this throat, we also have tension and torsion, but the tension is much slower than torsion, so the specimen will break here and not there or there. But so we have presented the other solution for only one tension torsion ratio. But what I want to present to you today is how we can do different shear to axial stress ratio with what must we change here in the booster, in the horn, or in the specimen in order to have different shear to axial stress ratio. And the solution is we will use always the same horn, because what we want to change here is the axial movement to axial rotational. What we are going to do is to transform the rotation, the shear here in this throat and throat, in order to have a differential throat shear between all over there. And this happens by just changing
these three dimensions, E, A, B, C, and the radius. So the radius E is the same there and the same there. But by changing A, B, and C with the same R, we can have different torsion stresses here, here, and there. Of course, the axial is always the same because it also depends of the length. So we have the axial here, and we maximize the shear stress over there by minimizing that one and that one. While on our first specimens, we have always the same shear stress here, here, and there. So you have some explanation about this, and this afternoon, Pedro will talk a little more about this in this paper. So let's see our results. So we have made this steel. This is a low carbon, but also low alloy steel. It's constant temperature, so it has some kind of Martin-Six structure. So we need to have the Euler-Young's modules in order to to have the dimension of the specimen and the shear modulus also, which is related with the Young's modulus, of course. And we have here three specimen design. In each one, we will have a different shear to axial stress ratio, because we have changes the A, B, C for the same radius. So we have tested this, and we are going to present some results. Okay, before the results, in order to see if you have the correct behavior of the three-throat specimen, we must determine the temperature in each throat. This is a methodology that we already have for axial ones. This is for axial one, there is no three throats. And this is the normal situation. This is a bad situation that was put there in order to see if our thermographic camera could detect higher temperatures. So for the three-throat specimen, here we have, okay, we have torsion here, we have torsion here, and some axial also, but the conjunction of maximum torsion and the maximum axial is on the main throat, so this is the fatigue region. So because we always control our temperature on our machines. Normally we don't go above 35 Celsius degree. So comparison, for uniaxial tension on ultrasonic fatigue, we have this behavior. We cannot have never failure in ultrasonic fatigue testing, because when we have a larger crack, we lost the resonance of the machine, and the steam stops. After this is broken on a normal uniaxial tension test. And for tension torsion, of course, this zone is much lower, because we have a conjunction of both stresses, and the difference between the shape of the crack is also different. So three different stages for three different shear to axial stress ratio. We have, of course, we have different crack proportions, but also we can measure the inclination of the initial crack, because it depends of the shear to axial stress ratio, as already observed in servo-hydraulic tension torsion fatigue testing machines. So we have also quite a lot of experiments in servo-hydraulic ones, and this is coincident. So we think that this is correct ones, either in ultrasonic fatigue or in the servo-hydraulic ones. And okay, some results. And we have divided this okay, we have put here on axial stress ratio, because it is that one that is always constant between the three specimens. So we have divided this where the shear to axial stress ratio is higher than the equivalent von Mises equivalent stress, or is lower. And we have two different behaviors. We could not have many tests over there for 10 power 9, because we only have a few tests yet. This is a study that is ongoing, but we see different behavior with this. And the second one also the inclination, the calculation angle according to the shear to axial stress ratio, again for higher shear stress than axial one, or higher shear stress the axial, or higher axial the shear stress. So there are two different behaviors. This is absolutely comparable with servo-hydraulic torsion testing machines. So we think we are on the correct solution for having in ultrasonic fatigue testing the three solutions for axial, for cruciform, or for tension torsion. So the conclusions. So we think that piezoelectric plate fatigue testing machines are working very well now. We are very confident with this. Only we must take care about temperature, frequency, and to have a data acquisition very good. We use strain gauges, we use laser measurements either for rotation or for axial. So in order to have axial torsion fatigue tests or cruciform fatigue tests, like we have seen in the presentation by Diogo, we use always the same piezoelectric plate. We only need to change the specimen and the order. So this is a very cheap test. We don't need to have a very expensive fatigue test. And we have achieved different shear to axial stress ratio with ultrasound just by changing the specimen geometry. So thank you for your attention.